Hello everyone. Today we are going to start our discussion of rendering. So what is rendering? Rendering is drawing any image to the screen, and we have already answered part of the rendering question when we looked at rasterization and at visibility. We already know which pixels to color. We know this due to our study of rasterization algorithms, which we started this course with. And we know this also from our study of visibility, where we figured out which objects are visible and which objects are occluded. There is another part to the rendering question, which asks what color should be used to color a particular pixel or fragment, and how do you apply this color to the pixel or the fragment. And you have to figure this out for all the pixels and the fragments that make up your scene. So in order to be able to do this, we need to figure out how does illumination travel in your scene. This requires us to model light sources. It requires us to assign surface properties to various objects. And then we need to figure out how does light bounce off from various objects before it reaches our sensor or the camera. So this is what we are going to study in this part of the course, and we are going to study all this inside the context of a rasterization model. Now let us begin by trying to understand what does it mean to model illumination in this context, right? What is the illumination model? So here is a rendered scene, and here you can see that the primary light source is this lamp on the desk. So all the points in the scene that receive light directly from the light source. So light emanates from the light source here, and it travels to various surfaces. And if we can see this point is the color that we see here, right? Or that is what influences the color that we see here. So the color here is actually a combination of the color of the surface and the color of the light source. So we'll get to that later. But the illumination that reaches a surface point directly from a light source is called direct illumination or local illumination. Okay. What is the other mode via which illumination can reach a surface point? Well, illumination can start at a light source, then it can bounce off from one surface and then bounce off from another surface before it finally reaches the surface that we are interested in. Right? So here, for example, on this part of the roof, perhaps the light bounced off multiple surfaces before it reached here. So whenever light reaches a surface point or a surface patch from another surface instead of directly coming from the light source, regardless of how many bounces it has had in between, it is called indirect illumination. Okay, and it should be kind of obvious to you that indirect illumination is harder to compute because you have to compute all these different kinds of bounces that the light ray might have. So the more expensive part of modeling illumination is the computation of indirect illumination. And indirect and direct illumination together are known as global illumination. So whenever you see somewhere that it is mentioned that we are modeling global illumination, what it essentially means is that we are modeling both direct and indirect illumination. For our purposes, we make a approximation to the light transfer computation. So of course, there is the best known physical model that might be out there for modeling light transfer is still some approximation of the real process. Okay, but let us assume that that best known physical model, whatever it is, maybe it is something that involves quantum mechanics. Let us assume that that model is the gold standard of light transport. Okay. Now, obviously, you cannot use that model to render your images, because that is going to be extremely compute intensive and may not even be tractable in any sort of reasonable amount of time. So we use further approximations to the light transport or illumination transfer phenomena, right? So this property of a light source emanating some radiance that travels from that source to surfaces to the camera sensor is known as light transport or illumination transport. So whenever I say these words, that is what it means. We will restrict ourselves to the abstract idea of illumination transfer as light bouncing around a scene. So by modeling illumination, what I mean is that we need to figure out how does light bounce around a particular scene, and because of this light bouncing around a scene, what kind of colors will we see at those scene points, right? So we will use some approximate model to represent our transfer of illumination from a light source to a surface to our camera. This illumination model that we are going to use is called a Phong Illumination Model. And this is a very simple illumination model. We will see for a single light source, total illumination at any surface point is given as Ka into Ia plus Kd into Id plus Ks into Is. Here Ia is the ambient component, and we will see what it means. Id is the diffuse component and Is is the specular component. So basically we have divided our illumination transfer model into three parts. Now let us try and figure out what are these three parts. So we will begin our discussion by looking at the diffuse component of this model. So the word diffuse is actually describing a surface property. So surfaces that reflect light that falls on them or is incident on them, so that is the technical term. So light that is incident on a surface, if the surface reflects that light equally in all possible directions, then that surface is called an ideal diffuse surface. What it means physically is that that surface is very rough at a microscopic level. Examples of such surfaces are chalk, clay, the plaster on your walls, and so on, right? So these surfaces have a very matte finish, so they are not shiny. Okay, we represent the kind of reflection that happens on diffuse surfaces by this diagram. So here we are showing the incident light direction by this red arrow, and notice the direction of this arrow is from the light source to the point on the surface, and yet we have labeled this direction as -L. So the reason we have labeled this as -L is because L, it is the position of the light with respect to the surface. So actually they are talking about the vector from the surface point to the light source. So that is the direction of L. Therefore the red arrow has been labeled as -L in the diagram. So in the formula, if you see L, that is the vector from the surface point to the light source. So given the direction of the light source and the normal to the surface, you can compute the diffuse component of illumination as IL cos theta L, where theta L is the angle the light vector makes with the surface normal. Now we know why the surface normal or the outward facing normal is important, because if this normal direction is wrong, then you will compute illumination incorrectly at surface points. Now let us see the behavior of this model when the light vector is in the direction of the normal, that is that they overlap, so the angle is 0, then cos theta L is going to be at its maximum. So you see that the envelope radius that you have here for the reflected illumination is large. As the angle the light vector makes with the normal increases, the radius of this envelope goes on decreasing. So the envelope actually represents all these rays. So these rays are all the directions in which light is being reflected. So diffuse surface is reflecting light in all possible directions. Hence this envelope is like a hemisphere. So the diagram that we are showing here is in 2 dimensions, but actually the reflection happens in 3D. So if you think about it, then the real diagram should be a hemisphere like this, right? So light is coming in some direction. This is the surface normal, and this is the surface patch, right? And light is being reflected out in all possible directions. Okay, so this envelope has a name. It is called the BRDF, which is short form for bidirectional reflectance distribution function. It tells you how the reflected illumination is distributed in space around the surface point, given the normal at the surface point and the direction of incident illumination or incident light. Okay, so given L and N, in what directions is the action happening? And the answer for a diffuse surface, or an ideal diffuse surface rather, is that it happens in all directions equally. And how do you compute it? You compute it as IL. IL is the illumination that the incoming light carries times cos theta L. And this cos theta L is also known as Lambert's cosine law. Therefore, ideal diffuse surfaces are also called Lambertian surfaces because they follow Lambert's cosine law. When you are computing the diffuse component of illumination, sometimes the surface might be facing away from the light source and the outward facing normal might be in the other direction. If that is the case, then L dot N will turn out to be negative. Of course, illumination that you register or measure from a surface cannot be negative. So when you do this computation inside a shader, and we will see exactly some shading code that does this computation, instead of using L dot N, you will use max of L dot N comma 0. So that if L dot N is negative, you return 0 instead. Okay. Another thing that you can add to this model is attenuation due to distance. So you can say that as light travels farther from its source, its true intensity goes on decreasing, and this decrease is a inverse square fall off. So instead of using IL, you can instead of saying that IL is the true intensity of the light source, you can say that the true intensity of the light source is IT, and IL is given as IT by R square, where R is the distance that the light has traveled from the light source to the surface point in question. Right? So this is the diffuse component of illumination. Notice that the diffuse component only depends upon the position of the light source with respect to the surface and the surface normal. It does not depend upon where you are looking at the surface from. So you can look at the surface from whichever direction you want, and you will perceive the same amount of reflected illumination, because the reflected illumination is the same in all directions. You can verify this. You can stand in front of a rough wall that is like whitewashed or plastered, and you can look at a small area on the wall from various directions. Just move around the wall a little bit, and you will see that it appears the same. Nothing much seems to change about the appearance of that flat